Hello, this is John Wallace, Senior Editor at Laser Focus World, and welcome to today's webcast brought to you by Laser Focus World Online. Today's event, Glass Processing for Fiber Laser Component Fabrication, will be presented by Doug Duke, Senior Applications and Development Engineer at AFL. Following the talk, we'll have a short question and answer session. You can ask questions at any time during the presentation via the web using your Ask Your Question box by clicking in the open area and clicking the Ask Question button to submit. And we will have Mike Harju, Application and Process Development Manager at AFL, with us, in addition to Doug, for the Q&A session. If you should need technical assistance, please type your inquiry into the tech support box on the left side of your screen and click the Send button. It's recommended that you close down all other applications for best performance. For your convenience, this presentation will be available on demand within 24 hours of this live event. A reminder email message will be sent to all registrants with the link to the archive. It will also be accessible from the home page at www.laserfocusworld.com. Now it gives me great pleasure to introduce today's speaker, Doug Duke.
Thanks, John. And I want to thank all of you for participating. We hope you'll find the information useful. So our subject today is glass processing for fiber laser component and indeed fiber laser fabrication. And we'll talk on four basic subject areas. I won't spend too much time, but a brief introduction to AFL and Fujikura. Then we'll do a review of fiber laser construction and components. And because it's very important to the success of building a fiber laser, we're going to spend some time talking about the heating methods that can be employed for glass processing and splicing together the components of a fiber laser. And then we'll talk about the fabrication processes themselves and some of the important issues relating to splicing. So again, I'm not going to spend much time on introducing AFL and Fujikura, but if you're not familiar with us, there's a few slides in here with some information. AFL was formed as a joint venture between Aluminum Company of America and Fujikura in 1984. In 2005, Fujikura became our sole parent company. And Fujikura has a long history with fiber optics, and together with Fujikura, we have worldwide manufacturing and customer support activities. So let's jump into the fiber laser construction and components. Here we see just sort of a brief introduction to a fiber laser, and a fiber laser uses a section of a rare earth doped fiber as a lasing cavity, and the lasing is initiated by stimulated emission in the doped core. Typically, multiple pump lasers are utilized to initiate the stimulated emission, and that pump power is initially dumped into a cladding that surrounds the doped core, but then it couples to the core. If we look a little bit more into typical schematic for a fiber laser, as you can see here, there would be a number of pump lasers which are represented on the left side of the diagram, each coupled to an individual fiber. Those multiple fibers are then tapered in a pump combiner into a single combined pump power output that couples through a critical splice the pump power energy into the doped fiber, which is represented in the coil in the center of the screen, which becomes the lasing cavity. That first splice, it's important to couple all of that cladding pump power. But on the output side, to the right of the fiber coil, it's important to maintain the alignment of the signal core, because that's where your lasing power is now going to emerge. In fact, after that, you typically have in many cases, a pump dump or some other means where you remove any remaining cladding power, so that hopefully all you have remaining after that is the lasing power in the signal core. And then you might have a mode field adapter, which serves the function of bringing that lasing power with low loss into the output fiber, which might be a smaller diameter. And finally, on the output end of the fiber laser, you have an end cap or a ball lens, which then controls the shape of the output beam. So here's a look at some of the components in a fiber laser. You might have an ExCon Lens on individual fibers to couple the pump diode power into the individual fibers. And you might have a ball lens or an end cap on the output end at the opposite end of the fiber laser. And in between, you're going to have a combiner that brings all the pump power, the power from the individual pump lasers together. And to make that, first you take a capillary tube and you taper that down to a smaller diameter. We call that a start tube. Then you load multiple fibers into it, each from their individual pump laser, and you do a secondary tapering operation. And then what you come out with at the end is, you can see the cross section on the on the lower right-hand side of the screen. So you can see a cross section of a 19-into-1 combiner that would combine the outputs from 19 individual pump lasers. And then there's also a cross section of a 6+1 pump combiner where there's a polarization maintaining fiber in the center and 6 fibers from individual pump lasers surrounding that. So these are some of the typical things that have to be created and put together to create a fiber laser. One of the things about the active fiber is it's almost always going to be what's referred to as a double clad. So there's an inner core, which becomes the lasing cavity. That's surrounded by an inner cladding where the pump power is initially dumped. And then there's an outer cladding, which in the case of the fiber we see here, the outer cladding is a low-index polymer, and so that low-index polymer helps contain the pump power within that cladding. One of the critical things about splicing this fiber is that you want to do as little damage to the inner cladding as possible. You want a very smooth, debris-free surface, because if there are any crack sites, debris, or contamination on the fiber surface, after splicing this fiber, what will happen is those damaged sites on the surface of the cladding will be sites where the pump power can escape. And in a worst-case scenario, after we recoat with the low-index polymer, it could literally catch on fire if you have enough pump power escaping. So it's very important to splice with very, very good quality to have a very smooth surface that's contamination-free. Many other fiber lasers, you might use an active fiber where the outer cladding is actually formed by a ring of air holes, as you see in this case. We would oftentimes refer to this as an air-clad fiber. This is also a fiber that presents very significant splicing challenges, because if you collapse the ring of air holes, then what happens is, again, the pump power can escape. And it turns out that most heat sources that we might use for splicing are going to cause a problem with this. Using a CO2 laser as the heat source is really the best method to splice this kind of fiber, and we'll discuss that a bit more later. This is just an SEM picture where you can get an idea of how small the glass webs are in between the air holes in that air-clad structure. So you can see this is quite delicate, and as I'm sure you can imagine, it's difficult to splice. So let's move on to some discussion of the heating methods for glass processing. There are 4 predominant methods. Probably the oldest method that's been used is flame. It's typically not used for splicing anymore, although it has been. It is commonly used for fused and tapered combiners. That's the most predominant method. But it's well suited for fixed use in factories, not really well suited for most other use, and we won't spend a whole lot of time talking about flame. Electrode arc discharge is the most common method for fusion splicing. It's been used since the late 1970s. And very inexpensive, easy to use, user-friendly, no need for gas supplies or anything like that. But the electrodes wear. There are issues with scaling it up for large diameters and problems with using it for tapering. And you will get some sort of deposits on the surface of the glass. Remember, we were talking before that, for example, when you're splicing a double-clad fiber, you want to maintain a very smooth, debris-free glass surface. So those are some of the issues with electric arc discharge. Filament heating or resistive heating has been used for more than 20 years as well. And it's scalable for different sizes of fibers and different applications. It's more prone or can be more troublesome in terms of leaving deposits on the fiber surface, but it's a well-established method. CO2 laser has only recently become commercialized. It's a more expensive system, but very clean. There are no contamination issues from the heating method, but there are eye safety and other considerations we have to consider. This is a little bit of more of an economic analysis of the four methods, and with electric arc discharge and filaments, the electrodes and the filaments are wear items. They're consumables, and they are life limited, and there's a cost with replacement, and so if you compare that to a CO2 laser, with a CO2 laser, your initial purchase price is much higher, but then your consumable costs and your maintenance costs are virtually nil until several years of use, at which point you would send the laser in to have the gas recharged. So those are kind of the trade-offs. Let's talk a little bit more in detail about a filament. So here you can see a diagram or a picture of a filament. You can see the fiber going through it. So again, it's a resistive element. So like a filament in a light bulb, it needs an inert gas environment to protect the filament from ablation. There will be some ablation of the filament over time in any case. It can be scaled for larger fibers by changing the shape or size of the filament, and you can change materials as well to change heating characteristics. So it can be versatile and adaptable. One of the things about the resistive element or a filament is that the heating element surrounds the fiber, and that means that you have to do the alignment using your camera or other means. You can observe at one point, but then you have to move it over to where the filament is to heat it. So if we talk about some of the advantages of the filament, it's scalable, adaptable, capable of high strength, and during its useful life, filament is relatively stable, and you can maintain your process control fairly well. Some of the downsides are the fact that you do have to change the filament based on application, and if you're doing tapering, especially of a capillary tube, the filament shape is such to heat the capillary tube evenly all the way around, you have to feed it through the side of the filament. That makes loading the capillary tube difficult. Filament replacement also requires alignment, and that can be tedious and time-consuming. So you've got a life-limited filament, relatively high replacement cost compared to electrodes, and a little bit more work to replace the filament than you do with electrodes. Filaments are a little bit unforgiving. If you apply too much power and overheat and stress the filament, you pretty much have to replace it. You need to keep it within the acceptable process limits for the type of filament you're using. The inert gas is critical, and you typically have to have it very close to the filament location. It can't be remote, so it has to move with the machine. The operator has to be careful when loading and unloading a fiber because the opening at the top of the filament is relatively narrow, and if you touch the fiber against the filament, you could damage it. And as we mentioned before, it's not really compatible with imaging at the point where you're heating the fiber, so you can't use warm imaging. Also, as we mentioned before, there are issues with the filament ablation and deposits on the glass surface. So this has been a problem for some of the users who are using this system for assembling fiber lasers. Arc discharge systems, very, very common, very simple, easy to use. Essentially, the two electrodes create a plasma field of superheated air, and that's what melts the glass. It can also be scaled somewhat similar to filaments, but in order to scale it for a larger fiber, you need to increase the size of the plasma field, and we can do that by increasing the gap between the tips of the electrodes. One thing that should be borne in mind about a electric arc system is that the path between the anode and the cathode doesn't go directly through the fiber. It's going to go either over or below the fiber. So as you can see in the photograph here, you're going to get some differential heating with this method. Now, for smaller fiber diameters, that's meaningless, but when you get up above about 500 microns, the differential heating, where you're heating the fibers more on the top than at the bottom, can become a problem. We'll talk more about that later. As we mentioned before, it's very adaptable. So, for example, if we're splicing a 60-micron fiber, we might offset the fiber vertically from the axis of the electrode so that we're in a relatively cool area of the plasma field. Whereas for a normal fiber, we might line the electrodes up with the axis of the fiber so it's in the center and the hottest part of the heating zone. And then when we get to a larger diameter, we might increase the gap between the electrodes so we've got a wider plasma field that more effectively heats a large diameter fiber. So again, it can be an adaptable system. One of the problems, or one of the things that's just in the nature of electrodes is that there will be deposits of vaporized silica from the glass fiber that build up on the tips of the electrodes. This is not something you can avoid. In fact, initially, when you put a new pair of electrodes in, you want to do kind of a burn-in on the electrodes so that you build up an initial deposits of silica so that the electrode heat output will be stable. So you go through a stabilization before you start doing anything critical. The silica deposits become less stable after about 500 arcs in the case of normal splicing. But the deposition of the silica becomes much, much worse when we use higher power and larger fiber diameters. And you can see in this picture there's an extreme example. This is actually something we generated just in our own internal testing. Obviously, electrodes in the condition you see at the lower right would have been replaced a long time before. But anyway, the silica deposits are something that have to be managed and understood when using an electrode-based system. One of the other considerations is conducting heat away from the tip of the electrode. So as we go to larger diameter fibers, we go to larger diameter electrodes that can more efficiently conduct the heat away, and we might also use heat sinks to pull the heat off of the electrode itself. Arc fusion systems are compatible with all the common calibration methods, whether it's offsetting the fibers and looking at how fast they self-center and relating that to the heating power, or the special arc calibration we see in the center, where we're basically going to heat the cleaved tips of the fiber and look at how the fiber rounds off due to the amount of heat applied, or the auto arc calibration at the bottom, where we simply heat a single fiber and look at how much it luminesces. Obviously, it luminesces higher with higher power and a lesser degree with lower power. So one of the good things about an electrode system is it's compatible with all these methods of maintaining the proper heat output. So some of the advantages: robust, forgiving for production, well-proven, reliable, easy to use, user-friendly, adaptable, compatible with methods of calibration. The electrodes are inexpensive and they're very easy to replace. But some disadvantages are the electrode. If you change the gap between the electrodes, you need to recalibrate. The electrode life depends on the application. Silica deposits become more severe as we go to higher power and larger diameters, and you will get some deposits on the fiber that will cause some damage to the or contamination to the fiber surface, although typically not as severe as what you might encounter with a filament system. There is some instability splice by splice due to the fact that the silica deposits change a little bit, so routine calibration is recommended. And you do have differential heating top to bottom because the plasma field is either curving over or under the fiber. Multi-electrode systems have also been used. Here you can see some schematics of some different systems. AFL has done quite a bit of testing with multiple electrode systems. Here you can see a 4-electrode and a 3-electrode system. These are all in the same plane, which means that the plasma field is expanded in one plane only. So this is a way of overcoming the problem of the banana arc that's going to differentially heat the fiber top to bottom. So that can be useful. And if you don't have the electrodes coplanar, you can expand the width of the plasma heating area as you see in this diagram and in the photo at bottom right. One of the well-known multi-electrode systems that's been commercialized is called Ring of Fire. It uses 3 electrodes and a 3-phase system. If the electrodes are coplanar, again, we are expanding the heating area in the plane of the electrodes relative to the 2 electrodes system. So that allows us to splice larger fibers, to in fact taper or splice fibers of 2 millimeters or more, which you really can't do with a 2-electrode system. But the electrode wear issues, even with multi-electrode systems, continue to exist. And here you can see a 2-millimeter fiber tip that was melted with a 4-electrode system with about a 30-second arc time. And you can see that there's a significant deposition on the 4 electrodes with just a single heating step. So that's just, again, in the nature of electrodes. So the multi-electrode system has some advantages over dual electrodes in terms of allowing us to get to larger diameters and being better for tapering and more uniform heating. And it shares some of the user-friendliness of electrode systems in general. But disadvantages remain in terms of electrode life, silica deposits becoming greater as the heating power becomes greater, etc., instability, and even with a multi-electrode system, depending on the type of glass or the diameter, you might have to change the gap, and therefore you might have to recalibrate when you change your setup. We have also enhanced a dual electrode system by oscillating the electrode tips up and down, and this is to avoid the problem of differential heating top to bottom. And we'll see a video here in a moment, and actually in this still image you can see the banana arc going over the top of the fiber. So in this video what you're going to see is the electrode tips that are glowing blue in this picture are going to oscillate up and down, and you'll see the arc jump from the bottom to the top and back again. And then you'll see a video clip of a transverse view of the fiber in the splicer. And during the initial stage of the arc, when we're just gently heating the fiber, the screen is almost black, but then you'll see the heating area of the fiber jumping from the top of the fiber to the bottom of the fiber. So we'll go ahead and roll that video now. So the electrode swing, again, maintains most of the advantages of a dual electrode arc discharge system and overcomes the disadvantage of the differential heating due to the banana arc. But again, most of the disadvantages remain as well, so I don't think we need to restate those. So let's move on to CO2 laser heating. With the CO2 laser beam, the heating method is really the absorption of the laser energy at 10.6 microns, and silica absorbs incredibly efficiently at that wavelength. In fact, the laser energy will be really absorbed by the outer part of the fiber, and then the heat causes vibration of the molecular structure, and that conducts the heat inwards. So it's very efficiently absorbed, and so this is quite a difference from some of the other methods of heating that we've discussed. So there is no ablation or contamination from electrodes or filaments, and that's a big advantage. Now, we can control the size and the position of the heating area by changing the shape of the beam with lens elements. So we can have a normal Gaussian beam. We can intensify it with a focusing element. We can use a cylindrical lens to make more of a linear heating area. There's various things we can do to control the shape and density of the laser beam. And we can direct the beam in from three axes if we need to. We're actually testing a system like this in our engineering group as we speak. So we believe there's some significant advantage for high-powered fiber lasers for using the CO2 laser. Again, as I mentioned before, one of the issues with these double-clad fibers is to make sure that we have a very smooth, debris-free surface of the cladding, and with the CO2 laser, we don't have any source of contamination from the heating source. So we're really limiting the deposition on the fiber surface very significantly. And that also plays out in terms of a benefit in terms of fiber strength. If we're not contaminating or getting debris on the fiber surface, then we don't have crack sites that weaken the fiber to as great a degree. So here you can see, comparing the CO2 laser splicer to an arc fusion splicer, significant benefits in terms of the strength. So there are analogous benefits in terms of being able to contain a lot of pump power for a high-energy fiber laser. This is just similar data plotted in the form of a Weibull plot. All of this data that we've shown is just normal laboratory data. It wasn't conducted in a clean room. We could get much better results if we used a laminar flow bench or a clean room. So some of the advantages of the laser: there's no heating element to have ablation or cause deposits on the fiber surface. The CO2 absorption is a relatively gentle process, so if we control and use just the right amount of heating, we're also limiting the amount of vaporization of the silica itself and the redeposition of silica onto the adjacent areas of the fiber. So we're going to limit our cladding power loss in terms of fiber laser applications. It also turns out that this method of heating is very good for air-clad fibers. It's very well, we can control it very well so that we avoid the collapse of the air-clad structure. And the laser system is compatible with all observation and calibration methods. Disadvantages, probably the biggest one is, well, let me finish up with the advantages. Essentially, we have almost no recurring consumable costs. The laser itself will typically have a life of about 20,000 hours, at which point you send the laser in and get it recharged, and then you can use it again. So every couple of years you might have to do that, perhaps every 5 years. So you've really got reduced maintenance downtime. There's no need to replace electrodes or filaments, no need to recalibrate after replacing the filament or electrodes, no need to align the filaments or stabilize new electrodes. There's no need for calibrations based on changing the size of the fiber or changing electrode gap or changing filament type. All of those things are avoided. And the laser output itself has excellent long-term stability. So there's just, in general, less maintenance and calibration downtime. There are some disadvantages. The initial cost of a laser is it's quite a bit more expensive than other heating systems, including the beam delivery optics. There are safety issues to be addressed, so you have to take care of that. It's large and bulky, so there's service and support issues that have to be considered. And there's also a short-term power instability that has to be addressed, and we'll discuss these details. So let's talk about the power instability. A CO2 laser typically has a power fluctuation of about plus or minus 5%. When you initially turn the laser on, the fluctuation is very rapid, and then it continues to fluctuate at a slower pace as the lasing cavity warms up. But this power fluctuation is due to the expansion of and contraction of the lasing cavity and resultant mode hopping. And you can see to the right here that the brightness of a single mode fiber is quite different if we're at the plus 5% versus the minus 5% on the power fluctuation. So that could cause some problems if it's not addressed. So again, a typical fiber laser plus or minus 5%, if we use closed loop power stabilization techniques, then we can cut that by an order of magnitude. And you can see the comparison of the stability plots of an unstabilized CO2 laser to one that has active stabilization applied. So how do we do that? Well, we use two feedback methods. One is that we can split off with a beam sampler a small amount of the output power of the laser and monitor that directly and use that for feedback. And so that's quite useful. But the other thing we can do is we know that the brightness of the fiber depends on the energy being absorbed by the fiber, so we can use the luminescence of the fiber as detected by the observation system, the camera of the glass processing and splicing machine, as a feedback method. So by using those methods, we can reduce the variability of the power, and you can see in this splice loss study that if we don't stabilize the laser, in the case of splicing 125 micron SMF, the splice results are quite erratic. On average, about 0.15 dB. By using stabilization, we cut that dramatically, and actually, if we're using core alignment and a stabilized laser, we have world-class splice loss performance. So again, some other issues with the laser are safety and maintainability. The laser itself is, again, very robust and will last for about 20,000 hours before it needs service. But at that point, you want a kind of a modular structure so you can remove the laser and send it in to be recharged. But probably the most most of the service requirements for maintaining a glass processing system are going to be what we refer to as the splicing head, which is in green in this diagram. So that has all the motors, the mechanisms, the V-grooves, the cameras, limit switches. So if we make that removable so that it can be sent in for service, then it's pretty easy to maintain the system. So these are the kinds of considerations you need to be thinking about if you're going to design a laser-based glass processing system, because overall it's quite bulky, and you don't want to have to put the whole thing in a crate and send it in for service. The other thing is safety. The CO2 laser itself is a Class 4 device, which means that it is hazardous in terms of both skin exposure and eye exposure. So you need to enclose the working area and use safety lockout switches to make sure that during operation the operator is not exposed to any of the laser energy. So that has to be a design consideration for a laser-based system. So let's move on to the actual processes and devices that we need to make for fiber lasing. There's splicing, tapering, and lensing, and input and outputs that we have to do for a fiber laser. Splicing considerations, I think we can kind of summarize it by we really need a lot of versatility. There's different fiber diameters we have to deal with. Sometimes we have to splice a large fiber to a small fiber, a bundle of fibers to a single fiber, etc. And there may be various alignment techniques that are needed: manual alignment, PC control, lateral, side view alignment, or end view. Here we're going to see a video of a 7-into-1 combiner that's already been tapered, and this is showing a cross-section of it. And it will appear on the left hand of the screen. It's about 300 microns or more in diameter, and we're going to splice it to a 220 micron multi-mode fiber. And what's important here is to get a good weld, but at the same time a relatively abrupt transition of the diameter, because that allows the best coupling of the energy from the 7 fibers in the combiner into the multi-mode fiber. So that's what we're going to see in this video. The next video I'm going to show you is quite a bit different. In this case, we're going to do something analogous to a splice, but this is an overclad operation. So you're going to see a 125 micron fiber move in from the left and a 300 micron capillary tube move in from the right. And during the first stage of this process, the capillary tube will advance from the center towards the left such that it's overlapping the 125 micron fiber. And then the 125 micron fiber, which is already inside the capillary tube at that point, will advance towards the right such that it's extending almost all the way across the screen in the viewing area. And then we'll apply a number of pulsed lasing steps so that we very carefully and in a well-controlled fashion weld the tube onto the outside of the fiber. So this is a beam is to provide a pump dump so that we can pull off cladding power near the output of a fiber laser. there are many other splicing applications we might need to engage in for a fiber laser. It could be splicing photonic crystal fiber, as you can see here, to a solid fiber. In this case, the right-hand fiber is a normal 125 micron polarization maintaining panda fiber. The left-hand fiber is 250 microns with a larger core, and it's also polarization maintaining. It's photonic crystal, so it has a hole structure. In this case, in order to line it, an in-view observation system was used, and then core alignment, which could not be performed with the side view observation, was used by power meter feedback with GPIB. So one of the things to think about with fiber laser construction is you might need to be able to access various methods of alignment and various methods of and various types of fiber for either polarization maintaining alignment or lateral alignment. So you want to have, as I said before, versatility. Tapering is very important for fiber laser construction. So there are two principal areas where tapers are used. One is the pump combiner, where we take multiple fibers and pull them into a single output. And the other is near the output end of the fiber laser, where we might use a tapered mode field adapter to take the lasing energy from a large diameter fiber and couple it with low loss into a smaller diameter output fiber. So there are many things to be considered for tapering. One is the maximum taper length. Another is what is the taper ratio, in other words, the ratio of the starting diameter to the minimum diameter that you need to achieve. A load cell can be useful for tapering because that allows you to understand the status of the glass. Is it semi-molten? Is it going into liquid phase, which would mean that you've overheated it and you won't get a well-controlled taper? We can use a warm image to look at the luminescence of the fiber during tapering and monitor what we're doing with the power. And there are various considerations for how we control the motors during tapering. So we might use what we call an auto-pulling mode, where the feed speed is set by the user and is constant, and typically we feed in from the right-hand side and we pull on the left-hand side. So by pulling faster and faster on the left, we taper down to a smaller diameter, and then if we keep the motor speeds at a constant ratio, we have the waste area where the diameter is maintained at a smaller diameter, and then as we slow down the left-hand motor, we up-taper back up to the original diameter. So the auto-pulling mode gives the best shape accuracy, but for faster tapering time, we might set auto-feeding mode, where the pulling speed is constant. Typically, we can achieve a 1 to 10 taper ratio with either of these methods. If we need a higher taper ratio, then we might use what we call an all-auto mode. So again, this is just showing a little more detail about the relative motor speeds, and the graphical user interface allows you to just input the dimensions of the taper profile that you want to achieve, and then the calculations are done behind the scene in order to achieve the proper profile. You might want to perform a linear taper, in which case the transition from the conical taper area to the uniform diameter area is abrupt, or perhaps sinusoidal, where we've got a little bit of a curvature in the transition. So all of these things can kind of be programmed in to the tapering profile. As we mentioned before, one of the critical aspects of tapering for a fiber laser is to make a combiner. So first we have to taper a capillary tube. And tapering a capillary tube, it's very important to apply the heat evenly such that when we taper the capillary tube, we achieve a truly round shape. And then we get good packing when we load the fibers into the tube. We put it back into the glass processing machine and taper the multi-fiber combiner down in the secondary operation. So here you can see a cross-section of a 7-into-1 combiner and also a 6+1 combiner that has a polarization maintaining fiber in the center. Here's some other combiners. As the fiber laser power increases, oftentimes this is achieved by adding more and more layers of fibers inside the combiner so that more and more pump lasers can be used. It's important to maintain good geometry during not only the initial tapering of the start tube, but also the secondary tapering. And if you do, then you can achieve the appropriate taper ratio and minimum loss of pump power. And here are some results that have been achieved with the laser machine. One of the other applications for tapering is a mode field adapter. Mode field adapter typically is created by the combination of two things. One is tapering a large diameter fiber down to a smaller diameter fiber. For example, tapering a 250 or a 400 micron diameter fiber down to 125 micron. And then we splice it to a 125 micron fiber that has been pre-treated. And the 125 micron fiber has gone through a process that we call teching, thermally expanded core. And basically, this is a well-controlled heating of that fiber in order to cause diffusion of the core and thermal expansion of the mode field diameter. So in essence, with a mode field adapter, we're tapering the smaller fiber. We're tapering the larger diameter fiber down to a smaller diameter, but we're thermally expanding the core of the small diameter fiber that we splice it to. And if we do all of this in a well-controlled manner, then we can achieve minimal loss in coupling the power from the large diameter fiber to the small diameter output of the fiber laser. We'll talk a little bit about lensing. There's various lensing shapes and operations that can be done: ball lenses, probes, elongated lenses, convex lenses. And again, typically these can be done under computer control with a graphical user interface, as you can see up at the top. For a ball lens, the simplest way to generate a ball lens is to take a cleave fiber and gradually feed it into a heating area such that surface tension of the molten glass pulls it into a ball shape. We might want to have a pure silica ball lens on the output of a single mode fiber. In that case, we might first perform a splice, then move the fiber over and heat again, pull some of the coreless fiber off, and then feed it back into the heating area so that we end up with a coreless ball lens on the end of a single mode fiber. And you can see that in the bottom sequence of drawings on this slide. I'm going to show first a generation of just a 1200 micron ball lens with a 400 micron starting fiber. So you'll see the fiber feed in from the right into the heating area, and gradually the ball lens becomes larger and larger. And we're actually rotating the fiber as we do this so that we can minimize any droop. I was going to show a splice and secondary ball lens video as well. In the interest of time, I'm going to skip that one, and we'll move on to a few other slides here. One of the other type of lenses that can be generated is an ExCon lens. What you see in the polished sample is essentially a conical tip created on the end of a fiber. If we want to do that with a heating process, we end up with a different tip shape, as you see on the right, but the beam characteristics can be the same. And again, these ExCon lenses can be used for coupling to a diode laser, such as a pump laser. So in order to do this, we use a somewhat different process. First, we splice two fibers together. Then we taper them until we get to a very small diameter. At that point, we pull the two fibers apart. And what you'll see is in the video is a ball lens will be generated with the left-hand side fiber, and we will use that as a radiating heat element to control the tapered ExCon lens that's formed on the right side fiber, because controlling that tip shape is very important. Okay, sorry for the delay. One of the last thing we'll talk about is making end caps for the output of the fiber. Most commonly, an end cap is just a lens element that is spliced on, and it might be significantly larger than the diameter of the output fiber. We'll see a video here of a 2 millimeter fiber spliced to a 125 micron fiber. And what is notable is that since we're using a CO2 laser to do the splicing, the fact that we're heating through absorption means that it's relatively easy to perform this. If we used most heating methods, the amount of heat applied for 2 millimeter would be far too much for the 125 micron fiber, and the 125 micron fiber would be vaporized. But in this case, because the surface area of the 125 micron fiber is significantly smaller than the 2 millimeter fiber, the lasing power that is appropriate for both 2 millimeter and 125 is almost the same. So we're able to perform this splice with very good quality. Okay, this is our last slide. It's just, again, about end capping. But as you could see from the last video, what's important is to get a very good transition from one diameter to the other. And for best beam quality, it typically needs to be a very abrupt transition, but we do need a good weld. And this is actually just showing some data of an M2 measurement performed by one of our customers. And up in the upper right hand, you can see the end cap that was used for this measurement. So again, it's very, very critical to control the way we apply the heat, and that's one of the reasons we spent so much time in this discussion talking about the heat source itself. At this point, I'd like to thank you for your participation, and myself and Mike Harju are ready to answer some questions.
Okay, we're now in the Q&A portion of the webcast. So to ask a question via the web, type your question into the open area of the Ask a Question box and click the Ask Question button to submit. I have to say those videos were amazing. I had no idea you could splice a 2 millimeter fiber to a 125 micron fiber. Anyway, the first question is the 3-electrode system an AFL solution?
We've experimented with 3-electrode and 4-electrode and even more electrodes than that. We do not offer a 3-electrode system. When we decided to develop our new glass processing machine, we had to make a choice. We finally narrowed it down to a multi-electrode system or a CO2 laser system, and we thought the advantages of the laser were such that it was compelling for us, and we've stopped actively working on multi-electrode systems.
Mm-hmm. Regarding the CO2 laser heating, 10.6 microns versus 9.4 microns, which is better and why?
We're currently using 10.6. We're probably going to investigate 9.3 or 9.4. That wavelength tends to be not as well commercialized at this point.
I guess, Sam, this is Mike. Perhaps I can step in and help out a little bit here. Which is better? 9.4 definitely will absorb better, but my understanding is perhaps there's not as much reliability data, and perhaps there's components, maybe mirrors, lenses, that type of thing, that perhaps are not commercially available at this time.
Okay. Is CO2 splicing with the coating on?
No. Typically, you're going to apply a stripping process just as you would for any other type of splicing operation.
Okay. How does splice loss compare between these methods? And also comment about polarization maintaining erbium doped fiber. How about for that kind of fiber too?
Well, maybe I can answer this one as well. Splice losses virtually identical between, well, when we're talking smaller diameter, okay? So there is no advantage to using a CO2 other than having a clean surface for, let's say, smaller diameters, and I'm talking telecommunication. Polarization maintaining and extinction ratio are actually slightly better when you're using a CO2. Remember, CO2 is absorption. It's, let's say, similar to a microwave oven rather than a resistive heater or an electrode, which is like a conventional oven. You're heating the surrounding area in conduction. So where the big advantage is when you're going to larger diameter. So what you can do is use that differential heating or that absorption to really heat the outside of the glass, and you can get much better beam quality when you're splicing perhaps something like a 400 micron fiber or something larger compared to an electroded system.
Mm-hmm. And this question may have been answered in the last couple of slides, but what is the best type of splicer for asymmetric splicing and why?
Yes, perhaps I don't understand the question very well, but asymmetric splicing. So with a CO2 laser, basically you can adjust the beam so that you can offset the beam, and that would allow you to do asymmetric splicing. I would imagine that you could do the same thing with an electroded system as well as a resistive element, but I have a feeling in order to get the offset that you want, it would be a bit more of a challenge.
Okay. If we're talking about asymmetric in terms of fiber diameter, then I believe the CO2 system is the best because the power almost self-modulates due to the smaller absorption area of the smaller diameter fiber. So it allows you to apply the appropriate power to both a very small and a very large fiber at the same time, as in the 2 millimeter to 125 example. I'm not sure if that's what the questioner's if that was the intent of the question or not.
I'll tell you what. Let's make an assumption here. Perhaps we're talking about different glasses. Let's say maybe a very soft glass to a silica glass. Let's say like a Z-bland. So you've got an extremely low melting point going to a fairly high melting point. With a CO2 and with absorption, it's very straightforward to do. Remember, absorption rather than conduction. So you're actually just heating the material rather than heating the surrounding area.
Interesting. Next question. What was the cladding diameter for the 9-micron example? And I'm not sure what the 9-micron example was, but you might know.
9 micron.
Yeah, I don't know what it refers to. So.
Yeah, unfortunately, I don't.
Well, I can move on to the next question, and maybe we'll get a clarification in the meantime. Have you spliced other materials that are not silica-based? Sounds like you have. You said Z-bland.
Well, that's still silica-based, but I have actually spliced plastic optical fiber.
Oh, wow. Okay.
If it's something that will absorb, then we can do it.
Yep. For pulling a taper, or any of these other operations, does gravity ever cause a problem?
Well, like you saw on the ball lens, gravity, depending on the amount of mass that you have there, one of the tricks that we use is to actually rotate. And the AFL mechanical design allows for continuous rotation. And so that's how you avoid what we would consider droop due to gravity.
Okay. So unless we get a clarification for that other question, we're out of questions, but I have a question of my own. Just curiosity. When you're dealing with the air cladding fibers and fibers with microstructures, do you have to align the individual air holes? And if so, how?
Well, you can. On some applications, you are required to, and there's two different methods you can use. You can actually go to the end view and do the rotational alignment, or if the air holes are structured that you can actually rotate in the side view and do what we would call like a profile analysis, so that you take a look for peaks in brightness, and then you would match two peaks in brightness of like the left fiber and the right fiber. I hope that I was clear on that.
Yes. So I do want to mention to our audience that these questions are all available to the presenters. So the person who asked the question that wasn't really answered, we can answer that in the future through correspondence. So thank you very much. And Doug, would you like to make any closing remarks?
Again, I want to thank everybody for participating. I certainly want to thank Mike Harju for helping with the questions. Mike's been developing a lot of processes with the CO2 laser machine, and if there are other questions we haven't got to, we will certainly look into providing answers to those.
Okay, well, on behalf of Laser Focus World and Penwell Corporation, I'd like to thank Doug Duke, Senior Applications and Development Engineer at AFL, and Michael Harju, Application and Process Development Manager at AFL, for today's presentation, Glass Processing for Fiber Laser Component Fabrication. This presentation will be archived within 24 hours and can be accessed from the homepage at www.laserfocusworld.com. A reminder email message for the archive will be sent to registrants, complete with a link to the archive. We thank you for joining us today and look forward to future webcasts.